All right, please accept the message that the meeting is being live streamed. I think we're ready to go.
We are ready to go. Awesome. And I will share my screen for a second. So welcome everyone to this final day of the WOW Physics conference. Today we'll have many more exciting talks. We will start in the first session with a talk on astrophysics given by Dr. Maria Lugaro, and a talk on atomic, molecular, and optical physics given by Professor Dr. Heather Lewandowski. My colleague, Professor Dr. Camilla Hansen, will chair the first session, so I will directly hand over to Camilla. Just one remark, if you have questions, you can ask them after the talk. And if you have a question, please either raise your hand and we will unmute you, or use the Q&A panel that you should see in your Zoom window at the very bottom to put your questions there, and then we will select the questions and ask them to our speakers. So thanks so much for joining today, and then I hand over to Camilla, and I will stop sharing my screen.
Yes, hello everyone. So we are very happy to have Maria Lugaro here telling us about how to make elements from carbon to lead. First, a little bit about Maria. So Maria got her PhD in 2001 from Monash University. And after that, she has been traveling around a lot. She has gotten several fellowships. And now she's currently working at the Konkoly Observatory in Hungary. Maria has gotten the ERC Consolidator Grant Radio Star, where they were looking at the radioactive nuclei produced in stellar nuclear reactions. And these are among some of her main interests, namely looking at the radioactivity in the solar system, in stardust grains, also investigating the slow neutron capture process, and in general, nuclear astrophysics. So Maria, we're very happy to have you here today. Please go ahead and tell us about your science and yourself as well.
Okay, I forgot to unmute myself, but now I should be good. Okay, you can see my screen. I'm just going to move some. Okay, great. Thanks a lot for the invitation. Thank you so much for inviting me here. It's really great to meet all these women and being given the opportunity of networking with people that I didn't know before. So this is great, and know about other people's work. And yes, so I'm going to talk about producing chemical elements in stars. And this is a very broad topic because there are many, many types of stars that produce many types of elements. So I decided to focus on one of my main expertise, which is what happens inside low mass stars. And by low mass stars, I mean stars like the sun, maybe a little bit bigger. So this is something that it's a bit close to us. So I will show you what will happen to the sun when it will die in 5 billion years. And I will show you what kind of elements it will produce and how this is relevant to understanding where the chemical elements come from, and even to understanding things like the formation of planets like the Earth. So I was asked to start with a little introduction about myself. So of how I came here where I am. And because it's been a bit of hopping around the world, I made this little schematic here because I was born in Italy, in Torino, and that's where I studied for my undergraduate degree and master. And then I was lucky enough to be able to move to Australia, to Monash University, to do a PhD there. And after that, my first postdoc was in the UK, in Cambridge. And after that, I basically started to apply for my own fellowship. And this is what I have done in the past 20 years. And luckily, I have been successful in doing that, so that my my path in science could proceed to different countries. So I moved to the Netherlands with a Dutch fellowship. Then I decided to go back to Australia, and there I received the Monash and then the ARC Future Fellowship, which led to a lectureship which I held from 2011 to 2014, when I decided that I wanted to go back to Europe. And my best choice to come back was this grant from Hungary, where I could build my group. And in 2016, as you already heard, I received an ERC grant to study radioactivity, so especially radioactive nuclei, how they are produced in stars. And I just wanted to complement this picture with a couple of photos that for me are a bit of like pillars of the beginning and to where I am now. And the first photo is when I was a little girl. I wanted to be a ballet dancer up until about the age of 20. I had no idea that I would be involved in science. I had no idea that physics would be my path. And then after all this travel around, I was very happy that my work this year was given the award for physics by the Academy of Sciences here. So this was something that I've been very happy about that happened this year in May. So basically, I just wanted to show that what happened from me as a little girl wanted to be a dancer to becoming a physicist. And what happened is that in step one here, when I was doing my undergraduate studies, I discovered that I loved the physics a lot, and especially the topic that I will tell you about. I hope I show you how fascinating it is, the research that I am able to do. So let's see exactly what I'm talking about. So this is the sun in 4.5 billion years. And this is a very nice, of course, artist impression movie of a star that is an AGB star, so asymptotic giant branch. And this will be the sun when it dies. What will happen? Well, it's a giant star, so it's very large, and it's a red star because it's cooler in the surface. And what you can see it shows strong pulsations. The pulsation drive a lot of winds, so a lot of material is lost from the star. Interestingly, these regions of the star are cool enough that there's a lot of dust formation, lots of molecules and lots of dust. You can see the little specks of dust here. We can see it in the flux of light from these stars. For example, this is the feature at 11 micrometer of silicon carbide. Now the movie is zooming out because the stars become a very fluffy, big object. There's a last final fast wind that pushes the material away and make kind of a void here. And then the central star is very hot. So there are UV photons from the central star that illuminate the material here. So we have what we call a planetary nebula, which has nothing to do with planets, but when they were discovered first, people thought they had something to do with planets. So the name remained, but it's actually the end of the star like the sun. And in fact, you can see in the flux here that the lines, there's a lot of emission lines because the material here is ionized, and so we have a lot of re-emission of photons. So this is a very nice picture, and maybe you find a lot of this picture of planetary nebulae because there's lots of many shapes and form, and they're very, very nice objects. But I am actually not interested in what happens in the outside of these stars. I am a nuclear physicist in some sense, and so I am interested in places that are very hot and very dense because I want to study nuclear reaction happening. And so to do that, I have to zoom inside, deep inside the star. And to do that, I will show you this other image. So this is the red blob star that I showed you before that is losing a lot of mass. And now for comparison, I show you the sun. So as you see, this is a giant star because it is 100 times bigger than the sun today. But what I am interested in is not as much this big fluffy envelope that is all mixing hydrogen in the outer layer of the star. I am interested in this tiny core, this little part of the star that is right in the middle of it, and it's where the reaction rates can happen, nuclear reaction can happen. So in stars, it's nuclear reaction that produce the energy against the collapse of the object. And in these specific stars, we have both the burning of hydrogen and the burning of helium. And this happens in shells that are above a core, an even smaller core that is degenerate, electron degenerate. So there's no more reaction, nuclear reaction happening in the core. It is just the product of the previous hydrogen and helium burning. But this is a structure that is quite complicated because we have a shell just on top of the core where helium is burning. Then there is a shell where hydrogen is burning, and in between these, there is something that we call intershell, because it's between the two shells, which is rich in helium. So this is quite of a complicated structure. But what is interesting for me is that the temperatures here in this region can reach up to 400 million degrees. In the sun, in the core of the sun, we reach about 15 million degrees. So you can imagine that I have much more playground here because there's many, many more nuclear reactions that can happen. The densities also are much higher than in the sun. So this is a really, really interesting place where we can study nuclear reactions in the universe. So how does nuclear reaction happen? This is actually quantum effect. So I mentioned that helium is burning in these stars that I consider. So imagine you take two helium particles and you try to fusion them together. What happens is that helium, as we know, is made of two protons and two neutrons. So when I try to stick these two particles together, there is a Coulomb barrier that's quite strong because the two protons don't want to get together. So first of all, I need somehow I need the nuclei to pass this Coulomb barrier so that they can get close enough together that the strong nuclear force prevail. And what is interesting here that classical mechanics require this particle to have enough energy to climb the barrier and get to the other side. But this cannot happen in stars. The energy is not enough to do this. We have to rely on quantum tunneling effect to be able to pass the barrier and to be able for these two nuclei to get close enough. There's another picture that I kind of like to illustrate this. We know by quantum physics that a particle is actually a wave with a certain probability to be in certain places. And so this is a simple explanation of this quantum effect, that actually there is a probability that the particle will pass through the barrier. And thanks to the quantum effect, we can burn helium particles together, and we can make the carbon in the universe, including the carbon that make our own body, is made in stars. Okay, so how do I actually study these processes? This is what I work on, the way I do it. I need 2 or 3 different inputs to my model. So I typically sit in front of the computer and run codes that make me reproduce what happened inside the stars. So I need, of course, to know what is the temperature and the density of each point of the star, because this is what drives the nuclear reaction. And this is complicated because not only, as I show you here, the structure of this star is not simple. There's many different regions, but also the regions are not static. They change in time. So I need to have a lot of data that tells me each point in the star, at each time of the evolution, what it is temperature and what is its density. But then it's even more complicated than this, because what happens in stars is that there's mixing between different regions. So I need also to know every time that I want to model which regions are mixing with each other. And this is important for nuclear reaction, because on one hand, I can carry more fuel to burn, but on the other hand, I can carry outside the product of my nuclear reaction. So this is very important. Then what I do on top of this background, I need to add the nuclear reactions. So I want to make a list of the nuclei that I want to study, the whole list of the nuclear reaction between them, and I need to ask my nuclear physics experimental theoretical colleagues to tell me what is the probability of each of these reactions. This is an example that is quite simple, but from just having a look at it, all of these are very complicated. There are a lot of nuclei that we can study. This one is just an example of some type of hydrogen burning. But you can see I already have to include maybe 20, 30 nuclei, and each of them will react with other nuclei with at least 2 or 3 channels. So this is a big network of equations that I need to solve. It's a big matrix. And then what do I get out of my models? Once I put the nuclear reaction on top of the stellar structure, I can get the prediction of how much of which nucleus is produced by each star. And then I can play with it. I can change the mass of the star. I can make the star rotate. I can do other physical property of the stars and see how things change when I change the type of star, the characteristic, etc. I need to, I want to mention my colleague, Caracas, who is at Monash University, because actually, I cannot claim that I'm doing the part 1 and 2 myself. We have been working for 20 years together, because she's more the stellar model expert, and I am more interested in the nuclear physics part of the story. So thanks to her that we put together our expertise and we can do these models in a quite sophisticated way. So what is the big picture? What do I do with this prediction of how much I produce of this element? Why do I care about having this prediction? Because then we can put these inside the big picture of the galaxy and how matter cycle in the galaxy. I showed you before that my star is this one here, is the one that will become a planetary nebula, but this is not the only way that a star can die. We have core collapse supernova from massive stars, and then we have binary system where we have other type of supernova. We have compact objects that can merge, and all these objects, they will produce different elements and throw them out when they die. When they eject them, they throw them out in the medium that surrounds the stars. In this medium, we have molecular clouds, which are regions that are colder and denser. And in the molecular cloud, there's the birth of stars and their planets. And then again, the stars evolve. They can take millions to billions of years, depending on their mass. And again, they will die and they throw out the chemical elements. And so this is a cycle of matter that has been happening in the galaxy, in all galaxies, and specifically in our galaxy for the past 13 billion years. So this is the ultimate aim. This is what we want to model so that we can understand which type of star has produced which elements in the galaxy and in our solar system. And this is what we did with this other work, with my other colleague, Chaki Kobayashi. And this is a paper where we analyze the origin of the elements from carbon to uranium. So we're going from very light elements to very heavy elements. And this is the second most cited paper of the year 2020. So if you're interested in the field, you can have a look at this paper, and there's a lot of details about how the modeling is done and what kind of stellar deaths are included, etc. I am proud of this. I want to show this photo because it's three friends and three women friends who have managed to really do something big, I think. And this is a plot from that paper that Chucky made. So this is her copyright. Everybody knows the periodic table. This is the periodic table. This is a fresh light on the periodic table, because what we want to show here is each element in the periodic table, from which type of star in the solar system it came, but not only in the solar system, but as time evolved in the galaxy. So basically, let's take chromium, for example. It has a tiny contribution from AGB stars. It is produced quite a bit more by Korkolab supernova, but type 1a supernova from binary system, they are the most producing of the ion peak elements. This is the red part. But if we take instead, for example, nitrogen, you can see that low mass stars like the sun, which here are shown in green, they produce most of the nitrogen, not only in the solar system, which is represented by this dotted point here. This is the time when the sun formed and the nitrogen abundance in the sun, but also in general in the galaxy, as it will be as of today, which is the end of the little box, and from the beginning of the galaxy. So for each of these elements, we can tell when it was produced, by which site, and how much in the solar system come from which type of stars, all in this one nice plot of the table. Now I want to focus on some elements that I am particularly interested in, and these are elements heavier than iron. As you can see, there's a lot of green in these elements. So my stars, low mass stars like the sun, produce heavy elements up to lead. Neodymium, cerium, barium, lanthanum, they are only produced by these stars. How do they do this? How do we get to elements that have mass like 140, like cerium, or lead, who has 208? How do we fission together enough nuclei to get to 208? That's a lot of reactions. And what we have to do is to have neutrons. The reason is that iron already has 26 protons. So the Coulomb barrier for all the elements after iron is too high even for quantum physics. The quantum tunneling effect is not enough for iron to capture a proton or to capture an helium nucleus. It's just impossible. I mean, it's not impossible, but the quantum probability is so low that it just doesn't happen. So how do we go around this problem? Because there are elements heavier than iron in the universe. Well, we take particles who don't care about the Coulomb barrier. Neutrons don't have a charge. They don't care how many protons there are in the nuclei they want to join, because they don't feel the Coulomb barrier. So this is the way to do it, is to capture neutrons. The problem is that you don't have neutrons available. Protons, you find them everywhere, but neutrons, they decay into protons in 15 minutes. So how do we have neutrons that we can make these heavy elements? One way is, of course, to have objects like neutron star mergers, where there are a lot of neutrons there, of course, by definition. But another way is to produce neutron by nuclear reaction. And I will show you a couple of examples of these neutron sources in the stars that I study. I just wanted to show something for fun, because when I talk about heavy element, people are often never heard of them, like palladium or strontium or tantalum, barium, indium. These are elements that people they never heard their names, but they are a lot of the elements that we need today in our industry, technology. For example, an iPhone, a phone requires 46 elements, of which half of these elements heavier than iron. So it is interesting to know where they come from and why they are here. So to produce these heavy elements, as I mentioned, we need neutron captures. Traditionally, there are two types of neutron captures. And this is a nuclide chart, which is, I have my own nuclide chart I work with here at the back. Here in the picture is all in one all plot, but for example, the Karlsruhe nuclide chart here is is divided in different parts because it doesn't all fit in something like this. I need something very long. So the nuclide chart, for people who are not familiar with it, is a kind of extension of the periodic table. The periodic table helps us to understand the chemistry, how an element behaves in chemistry. The nuclide chart tells us how an element behaves in nuclear physics. And the reason is that here, plotted are both, each nucleus is plotted relatively to its number of protons. So when we increase vertically, this is all different elements. So we start from hydrogen, helium, etc., oxygen, calcium, nickel, etc. But we have an extra dimension here. We have the number of neutrons too, because elements have different isotopes, which means that they have the same number of protons, but different number of neutrons. And this chart allows us to see all this diversity. So the black boxes here, they are stable isotopes, and the other boxes are unstable. So we have two different types of neutron capture processes, and they both more or less start from the region of ion. Because that's where we need to add neutrons to continue to produce elements. So the rapid neutron capture, we believe that one site is neutron star mergers. These we have heard of the famous neutron star merger coincidence event with kilonova, which is a special type of star that produces a lot of light due to the decay of elements that are produced by the rapid neutron captures. Also, special type of supernova also can contribute to these rapid neutron captures. What I am interested in is what happened in my stars, the low mass stars like the sun, and this is called slow neutron captures. And how that can happen is because I can produce neutrons in my stars by some reaction. For example, nuclei of carbon-12, of carbon-13, which is an isotope of carbon, can capture alpha particle, helium-4, and their preferred way to deal with this interaction is to separate in oxygen-16 and a neutron. So I have 3 neutrons in my low mass stars, and so I can have neutron captures. Let me show you in a bit more detail exactly how it works by zooming in on a little bit of the nuclide chart here. This is the part of the nuclide chart that goes from ruthenium to silver. And the slow process happens, of course, by capturing neutrons. So I start with something stable like ruthenium 100, capture a neutron, I make ruthenium 101. And then I keep on going, ruthenium 102, but then I produce something that is not stable, ruthenium 103 decays in 40 days. The S process is called slow because the neutron capture is lower than the beta decay. So the path is basically just following the black boxes. For the rapid process is the opposite. Neutron captures are faster than decay, and so I continue and go out of this zoom here because I have to go here to where the rapid neutron capture path is. So it's a opposite process. what I want to point out here, because I want to use it in the last part that is coming up of the talk, is to note something. Palladium-110 cannot be produced by the S process, because when I reach palladium-109, this nucleus is quicker to decay than capture a neutron. So this is not produced in my stars, absolutely. Palladium-104 instead is strongly produced by the S process. The S process path goes directly inside this nucleus. So I produce palladium-104. Let's keep these two in mind. 104, yes. 110, no. And why this is interesting? So this is the solar system. And what people have been discovering in the past 20 years, but there's been more and more data, say in the last 10 years, is that if you measure the palladium isotopic composition of meteorites that formed farther away from the sun and the earth, you find higher palladium-110 and lower palladium-104. This means that the earth is more rich in material that was affected by slow neutron capture process. So there was in the disk from which our planets formed a richness of slow neutron capture isotopes as we were going towards the Earth. In other words, there was a richness of stardust from my stars. Do you remember the movie that I showed you at the beginning? All that little dust that was coming out, it ended up, some of this dust ended up in the place where the sun formed, ended up in the disk from which the planet formed, and was somehow distributed so that there was more of it where the Earth formed than outside. This is, I think, is very fascinating. And there's no clear, there's no consensus and clear explanation of what happened. This is the idea, some speculation of what could have happened. We have this dust that I show you in the movie also formed around the AGB stars. It is mixed in the medium from which other stars like the sun formed. But in this medium, there's more dust formation. And then when we end up in a disk, that was my timer, but I'm almost there. When we end up in a protoplanetary disk, dust that is easier to destroy when the temperature is hotter, so closer to the sun, should have been the dust that formed in this situation. So it's not carrying the S process signature. The dust that is carrying slow neutron capture process signature is this red one that is harder to destroy, is more resistant, this type of stardust like diamonds and gems. And so it survived relatively better closer to the sun than the other type of dust. And so this is why we are sitting on an Earth that is enriched in slow neutron capture isotopes that were carried by material from a star that was dying, from a Loma star that was dying. So I think this is just the beginning of a new era when we can use information about nuclear physics and nuclear reaction in stars to understand how a protoplanetary disk can evolve and how planets form from which type of matter. But this is just the beginning. I find it very exciting, but for the moment, there's no clear modeling of all these processes. I have a summary, but I think I'll skip it because I'm just going to repeat what I just said because I want to finish with this figure. This figure I like because it tells you what type of star we are coming from. It tells by mass the percent of which element make up our body. So if you weigh 100 kilos, 65 of your kilos are oxygen, and oxygen is mostly made in Corcol-Lab supernova. So big, massive stars that explode at the end of their life. About 20 kilos of you, it's carbon, of which a lot of it come from AGB stars, low mass stars that die. Hydrogen is 10 of your kilos, and this is from the Big Bang. So the hydrogen that is in our body comes from the beginning of the universe. And nitrogen is about 3%, and it's fully from the low mass stars. Then, of course, there is a few percent and traces of other very interesting elements. For example, iodine, probably coming from neutron star merger. So we have a little bit of a neutron star merger in our body. I thank you for the attention. I'm happy to take any questions. Thank you.
Thank you very much, Maria. So now it's open to questions. Please go ahead and drop your questions or raise your hands. We have one question, but I think maybe you have answered it, but I'm going to ask it anyways. It was asked in the question form, what are those barriers? So you were talking about the quantum tunneling barriers that would allow the reactions. I think you touched on this, but maybe if you can give a short comment on this, Maria.
Yes, so you mean it's the Coulomb barrier. Yeah. It's because protons are charged. So if you try to put a proton with a proton, it doesn't like to do that, right? It's two charged particles, they charge plus. So you have somehow to be able to get them close enough that then they can feel the strong neutron force. Is this answering the question? People can let me know if it was another aspect. I'm not sure.
Okay, in the meantime, I would have a question for you, Maria, if that's okay.
Yeah,
so
yeah.
Focusing mainly on the AGB stars, but I also know that you can have dust from different other events, right? You can also have, I don't know how much we get from supernova, and you can also have it from the massive fast rotating stars. Could you say something about what you would expect to see in which quantities in the solar system, for instance?
Yes, so this is a very interesting question. So what we have for sure is the stardust that we find in meteorites. That one for sure exists because we find it, we take it to the laboratory, we analyze it, and we see that it has the signature of where it came from. Of this dust, we have that the vast majority show the signature of coming from AGB stars, these stars that I've been talking about. And this makes sense because we know that these stars are the major dust producers in the local universe and in the local part of our galaxy. Then there is a big debate how much dust core collapse supernova produce, because they can produce it, but then maybe their shock can also destroy it, is unclear. We know that they produce it, but we don't know how much exactly. But we also find definite stardust from core collapse supernova in the inventory of the solar system. It's not a lot, there's very little of it, but it's definite that it exists. Other type of sources, as you say, could be like novae, for example. Novae can also produce dust. There's been found a few of that, but it's not that definite. And other stars that can produce dust, there's not many other, because, for example, the winds of very massive stars, they have a lot of UV photons. It's not a good place to form dust, because you form it, then the UV photons are very energetic, they would break it. Some interacting binary winds have been observed to be dust rich. But I think we stop here. Like, some people are trying to explain some anomalies using, for example, nucleosynthesis that can happen in thermonuclear supernovae, but these don't produce dust. Neutron star mergers, they don't produce dust. It just, to make dust, you have to be cooler than that. Too much energy, you don't condense into dust. So it is a debate at the moment, but in my opinion, as in this plot that I showed here, for example, I would focus on the low mass stars and the core collapse supernova as most prolific sources of dust. But it is an open topic. It is quite controversial. Yeah.
Okay, thanks a lot, Maria. I think we have one hand raised, so maybe we can make a quick question before we continue. Christina?
Thank you very, very much for letting me asking the question. Maria, you are great. I love your presentation. I love your slides. The enthusiasm is so big. It's extraordinary. What I want to ask you is about this red giant. The sun will be a red giant in some milliards of billions of years, and we are going to be maybe inside with our planet. Do you have any calculations of the density of whatever will be as coming from the sun and inserting the Earth inside this plasma, or what it is? And what will be the temperature at that time? Thank you so much.
Yeah, okay. So this is actually quite of a topic in the literature, of course. It's a very interesting question. So lots of people are looking into that. Even before becoming an AGB star, when the sun will become a red giant, if you want to help me, Camilla, feel free, because this is it's a controversial topic and I'm not too expert on this. I think people are debating, but it's quite clear that already when becoming a red giant the first time, the sun will incorporate the Earth. And then, yes, the surface temperature of these giant stars, they are maybe 3000 Kelvin, something like that. So it will be pretty hot already, just being at the surface of it. I am not sure if people at this point, if they think that the Earth will just spiral in and get closer and closer to the core of the star, or exactly what is going to happen. But my understanding is that we pretty much think that it is going to be the end of the Earth as well. But do you know anything better, Camilla?
No, I think that sounds pretty good.
Yeah, but there is a huge literature. I can find some paper and send them over for more details, because it's not like it's a big topic, and yeah, I haven't done work myself on these, though it's interesting to know what will happen.
Thank you, great work. Thank you.
Thank you.
So thanks a lot, Maria. This was really exciting, and it's always nice to hear your talk. So with this, I think we continue with the program, and I'll pass it on.
Thank you. I just stopped sharing. Okay, thank you so much for the question and for having me here. Thank you.
Thank you very much. So we move on right to the next talk.
Sorry.
Yes.
I need to jump in. Laura, can you turn off the YouTube recording and such that I can start it again?
Okay, and there's also another comment is our next speaker, Margaret Gardell, is in the audience. Maybe you can also make her a panelist.
Yes.
Yes, okay, perfect. And then, yes,